Welcome to Chapter 9, Linear Momentums and Collisions. I am Sorasak Phanphak. I will give you a lecture today about the whole things about the linear momentums and collisions. This is a part of General Physics 1, 01420111. From Kasetsart University, Bangkok, Thailand. We will know that what quantities that we look after in like several things that we already state, and this is one of them that we would like to quantify the motion of the object that have velocities. If those objects have velocities, you can determine with the one another definition we call the momentums. The momentum is what we quantify particle that has mass with the velocities. We multiply them so that we have the quantity state, the behavior of moving objects. Since you know that if object has the velocities, it's going to have the kinetic energy. But in this case, we focus on the momentums. Since the mass is the scalar and velocity is the vector, so the momentum finally is the product between scalar and vector. You're going to get a vectors for momentums. So to do the operation, like if you would like to add individual momentum together or subtract them, so please do with the vector operation. So you can multiply them, you can plus them. So use the vector for calculating the momentums. And the unit of the momentum is in kilogram meter per second. Since the kilogram come from the mass and velocity has the unit as a meter per second. There are several examples of momentums in our everyday life, mostly in the sports. And when you're driving a car, if the car has the speed or velocities, and you inside the car, you get the momentum from the car. This is the first example. If you look after the ball that reaching the baseball bat, why this guy swing the baseball bat in this direction, you will see the moment immediately before the baseball hitting the baseball bat is what we can state that this even have two different momentums. The first one is momentum from the ball itself, and the second one is the momentum from the bat. However, this is what happened before a collision, before this guy hitting the ball. But what happened next? When this bat hitting the ball, you can see the bat has some velocity and the ball also has another velocity. We call this the terminal velocities. Since we're gonna write initial velocity as Vi and terminal velocity as Vf, or we may use V1 and V2 for the initial and terminal, right, in two different states. However, with this and you sum with the mass, the total momentums from the first event before collision, and this is the after, the sum of momentum should be exactly the same. This is under the conservation of the momentums. We will learn about this later. Another example showing this is also another conservation of momentums. You can see two balls drop with the same speed initially. After hitting the surface, the ground surface, momentum change. And when momentum change means they try to conserve the momentums. So if this ball have really small mass compared to another one with a more heavier mass, the smaller one will shoot up with the bigger magnitude of velocities compared to the bigger ball ones. You can see is rising up with a smaller speed here, as you can see. Another thing is when you bowling things, for example, in this case, this robot tried to bowling, the terminal velocity when the bowling hit the bowling pin, as you can see here, these are bowling pin. Initially, they stay still. All velocities and momentum come from the bowling ball. After bowling ball hit those pin like break through and scatter like everywhere. So this is look like random things that happen. However, it is still under the conservation of the momentum. I will write like sigma pi equal to sigma pf. I will try to explain about this thing later, and you will learn more and more about all those things evolve around the conservation of momentums for this chapter. If you have the mass this object m like this, the blue object is moving in 3 dimensions with the velocities, and all velocity is in vectors. If you multiply with the mass in like this, you will get your momentum in 3 dimensions. This is how you use the knowledge of vectors operation. You have the scalar product multiply with the vector, and you still have the vectors. We know that the momentums is the quantities that we try to describe the particle or object that moving with the speed. However, the momentum can be derived from Newton's. We can see some relation between the second law of Newton's to the momentums or the chain of the momentums with the times. So, as you know that the mv is the quantities that we call as a momentum. So if we look into the second law of Newton's, so is sigma F equal to ma, or net force equal to ma, and a you can change to dv by dt. You know the definition of that. And if the mass is constant in this case, so you can move mass inside the blanket and this dip mv, and this mv is your momentums. With this relation, you can see that the change of the momentums by the times is the net force. And this is what happened. The change of momentums we later call the impulse. So that means the change of the thing that's moving, and you have the speed change. Or further, you will know that the mass can be changed in like jet propulsion system or in the rocket propulsion system. However, in this case, with the rate of change of the linear momentums, with the terms, with this definition, is the net force that acting on the particle. If you look after this example, the reason is you should wear a helmet while you cycling or riding a bicycle or even a motorbike, because it can save the way that your brain impacts when you hit on the ground. This is on the even on the water surface. When you're wearing the helmet like this, that means you spend a longer time that before its impact to your skeleton and hitting your brain. So if you have the time more, so you have lower impact force acting on your brains. However, if you're not wearing any helmet or buckle like this, you reduce the time that delay the impact of the chain of the momentums. That means you increase the impact force into that act to your skeleton or your brains later. This is how you use the chain of the momentum to explain the safety in our daily routines. So if you would like to be more safer, just wearing a helmet while you skateboarding or riding a bicycle. We did say about the conservative of linear momentums already, but what I have to say, like you have to consider about the thing that happened before a collision and after the collisions, or even between that total uh, linear of momentums, gonna be exactly the same. This is an example of the isolate system. We did learn about the isolate system, that the system have no external force. In this case, there's no external force involved. So the thing that's happened is only due to the initial speed or initial momentums of the system that you look after, and the final state of the momentums that you look after the collisions. This is an example. If you look after this guy, he have the white snooker ball traveling with speed before hitting with another color, which is I think red one of the snooker ball. And after hitting, the change of momentum change the direction of these two snooker ball motion with different speed. However, the total momentum from the event, this is before a collision and after collision, it should be the same due to the conservation of linear momentums. And we will investigate this more through the example. This is our first example. This guy, the archer guys, about to shooting the arrows out of this bow. Since you can see the floor that he's standing now is in the icy one, so this means the frictionless floor. So with the third law of Newton, if you have the action force, it should equal to the reaction force. That is the thing that when you have the momentums of arrows come out with mv, the net momentum should be exactly the same. So what happened here? Initially, this guy, he stands still, right? Not shooting the arrow yet. So that means the arrows also have the zero speed, or even this guy also have zero speed as well. This is the first before the change of the momentums. However, with the isolate system, there is no change of the momentum because there is no external force. Since you know from the previous section, the net force is come from the change of the momentum by the time. Right. So look after the second event. So when this guy shoot out the arrow from this bow, I mean the arrows go out with the velocity, in this case 85 meters per second. So it's carry out momentum with the mass of arrow. So if you like to conserve the momentums over here, which is the initial net momentums is zero due to the initial velocity is they are zeros. So that means you should have another momentum pointing backward. This should be another momentum. And this is the momentum of the archer guy. And this is the momentums of arrows. So now, since we know that the momentums is mass multiplied with velocity, don't forget that momentums and velocity, they are vectors. We will do perform calculation here. If I state that let this direction as a positive x or in I direction like this, if it have the negative sign, it should go backward for minus x. With this case, we can perform at a scalar calculation, doing a calculation, but remind you that momentum is a vector. So we now apply with the conservative law of momentums, which is the sigma pi or sigma p1 equal to sigma p2 or pf. What happened initially, the net momentum is zeros. And finally, what is happened should have the momentums of the arrows plus momentums of the archer guys, the sum should equal to 0. Now you're gonna substitute mv in, so that this is m arrows, v arrows plus m archer, v archer equal to 0. What you would like to find now, you would like to find out the velocity of the archer crossing this icy floor. So you would like to know these quantities. So you can rearrange the term if you want. So you can rewrite like archer equal to minus, because change this to another side, arrow, v arrow, and divide by mass of archer. I will sub all the quantities in, since mass of arrows is 0.03 and velocity of arrows is 85, and you divide with the mass of archer, which is 60. Finally, you're gonna get the value out for the velocities of the archer is minus 0.042 in meter per second. The reason of the negative sign is because this guy was kicked back by the momentum of the arrow. So this is the momentum of the archer. This is from the arrow. And as I said, the momentum is vector and velocity is vector. You can re-identify or redefine this as a velocity quantity as well. Rather than you write v equal to 85, you can write it. I suggest you to write like v equal to 85 in I direction, which is meter per second. Since you identify it as a vector, you can put everything in as a vector. Think of these momentum as vectors. Velocity also vectors. If you would like to find the velocity of the archer, and you know that the velocity of arrows is a vector, this is 85 in I direction. And finally, you're gonna get minus 0.042 in minus I direction. The unit is meter per second. This is how you use knowledge of the momentums, which is a linear momentums, and with you apply with the conservation law motion, and that how you can approximate the speed or velocity of the archer when you shoot out the arrows on the icy floor.